The universe is a place of immense beauty and staggering violence. When we gaze up at the night sky, we see a serene, peaceful canvas of twinkling lights. But this apparent calm is an illusion, a trick of the vast distances that separate us from the action. Out there, in the cosmic darkness, stars are being born, and stars are dying in spectacular fashion. These stellar deaths are not gentle affairs. They are some of the most powerful explosions the universe has ever known. For centuries, we have been captivated by these cosmic fireworks, events so bright they can outshine entire galaxies. For a long time, our understanding of stellar explosions was neatly divided into two main categories. On one end of the scale, we had the mighty supernovae, the complete and utter destruction of a massive star. On the other end, we had novae. A nova, which means new in Latin, is a much less dramatic, though still incredibly powerful event. Instead, it happens in a binary system, where a dense, compact star called a white dwarf orbits a larger companion star. The white dwarf's powerful gravity pulls material, mostly hydrogen, from its partner. This material builds up on the white dwarf's surface like snow piling up on a mountain. Eventually, the pressure and temperature at the bottom of this layer reach a critical point, igniting a runaway thermonuclear explosion. The first hints of something new came from the data. Modern astronomical surveys, like the European Space Agency's Gaia mission or the Zwicky Transient Facility in California, are incredible machines for discovery. They scan the entire sky over and over, night after night, taking digital snapshots of billions of stars. And among the flood of data, astronomers started noticing a new type of event. It was a brief, faint flash of light, lasting only a few hours before fading back into obscurity. It was a cosmic puzzle that defied easy explanation. These flashes were 1,000,000 times less powerful than a typical nova. A nova can be seen with a good pair of binoculars if it happens close enough in our galaxy, but these new events were far too faint. They would be completely missed by all but the most sensitive modern telescopes. This is where the story of the Micronova begins. The name itself gives you a sense of the scale we are talking about. It is not a super explosion or even a regular one. It is micro, a tiny localized blast on the surface of a star. The theory that emerged to explain these flashes was both elegant and surprising. Some of these white dwarfs have incredibly strong magnetic fields, billions of times stronger than Earth's. These powerful magnetic fields can channel the stolen hydrogen gas, funneling it directly onto the star's magnetic poles. Instead of forming an even layer across the whole star, the material piles up in a confined area at these poles, almost like a giant cosmic mountain of hydrogen. Eventually, it reaches the tipping point for a thermonuclear explosion, but it's a contained one. The resulting blast is confined to just one small region of the white dwarf's surface, a micronova. The crucial tool that unlocked the mystery of micronovae was NASA's Transiting Exoplanet Survey Satellite, or TESS. Although TESS was designed primarily to hunt for exoplanets, its method of doing so made it the perfect instrument for catching these tiny stellar explosions. TESS works by staring at large patches of the sky for about a month at a time, continuously monitoring the brightness of hundreds of thousands of stars. The team of astronomers, led by Simone Scaringhi at Durham University, had a theory about localized explosions on magnetic white dwarfs. They suspected that these events might be happening, but they needed definitive proof. They turned to the vast public archive of TESS data, a treasure trove of stellar observations available to scientists all over the world. In the data from a star system named TV Columbi, they saw a clear, unambiguous spike. The star's brightness shot up for a few hours and then quickly faded. It was too short to be a nova, but its profile matched their theoretical models of a contained thermonuclear explosion perfectly. They had found their first smoking gun. The discovery of a new cosmic phenomenon is always exciting, but the real importance of micronovae lies in the problems they might solve. For decades, astronomers have wrestled with certain puzzles in their understanding of binary star systems. The problem is, when we look out into the galaxy, we don't see nearly enough nova explosions to account for all the material being accreted. Where was all the missing hydrogen going? Micronovae offer a beautiful and elegant solution to this long-standing mystery. If many magnetic white dwarfs are funneling material to their poles, they would burn it off in a series of small, rapid, and incredibly faint micronovae. Think of it like a dripping tap. A classical nova is like waiting for the entire sink to fill up and overflow in a huge splash. Micronovae are like a tiny hole in the bottom of the sink, letting the water drain out in a constant, quiet trickle. We are at the dawn of a new field of study. The next generation of astronomical surveys, like the Vera C. Rubin Observatory, currently under construction in Chile, will be transformative. It is expected to detect thousands, if not tens of thousands, of transient events every single night. Among this deluge of data will be a treasure trove of micronovae. Several big questions loom large, guiding the direction of future research. Perhaps the most fundamental question is, just how common are micronovae? Another profound question concerns their role in cosmic alchemy. Astronomers will need to use spectroscopy to search for the chemical fingerprints of newly created elements in the ejected material. The romantic image of an astronomer is often one of a solitary figure, perched high on a mountaintop, peering through the eyepiece of a giant telescope. Today's astronomer is more likely to be found in a brightly lit office, staring at a computer screen filled with data plots and complex spreadsheets. The discovery of Micronovae wasn't the work of just one brilliant mind, but the result of a collaborative international effort spanning continents. For any scientist, there's this unique and profound excitement that comes with seeing an idea confirmed by reality. This is the thrill that fuels a scientist's career, the successful culmination of a long and difficult hunt. The people behind this science are driven by a fundamental human desire to understand our place in the cosmos. They accept the challenges and uncertainties because the potential reward is so profound. Micronovae force us to rewrite the final chapter of stellar evolution. They reveal a far more active and dynamic afterlife for many stellar remnants than we ever imagined, showing that the story of a star doesn't just end when it becomes a white dwarf. Each micronova explosion is a tiny thermonuclear reactor. While a single micronova produces only a minuscule amount, the sheer frequency of these events could make them a significant contributor to the galaxy's chemical budget over cosmic time. The night sky may look peaceful and unchanging, but we now know it is alive with a secret fire, a constant flicker of tiny explosions happening on stars millions of light years away. It is a universe of constant surprise, and our journey of discovery is just getting started. The same curiosity that led us to find these micronovae will continue to drive us forward. Because if there is one thing we have learned, it is that there is always something new to be found, waiting just beyond the edge of the light. The discovery of micronovae shows that even the most familiar subjects still hold profound secrets. It is a powerful lesson in the value of looking closer, of paying attention to the small signals, and of never assuming that we have the final answer.